This is a new lecture for the new lecture for the video. Yeah. I think we should start. Good morning, everyone. The final round, and this is really also the last set of slides I have. So we want to talk about modeling, and really, because we said most of the things about the physics already, modeling doesn't teach you much new stuff, because it's really just taking many of the things we already said and putting them in a model. So I want to start out by talking about different methods that you would find in CFD codes. And I just want to go briefly over these, but these would be maybe standard models where you can just click on a button in a commercial code which you can use then. So then I'll talk a little bit about statistical methods. We talk about definition here of PDFs and CDFs and averaging and so on. So that is quite useful if you don't have that background. And then we talk about different models. One model that is very popular is the transported PDF model. I want to tell you what that is. Then we'll talk about a few models here for premixed combustion, and then we talk about models for non-premixed combustion. So we start out with the vector here of reactive scalars. We introduced this yesterday. This here is all mass fractions and temperature which are in the system, and they are described by an equation like this. And I mentioned this equation here assumes that the Lewis numbers are, actually this does not assume the Lewis numbers are 1, but for the temperature equation there would be some terms missing here. But if you, this is just for illustration purposes, if you want to add these, if you really want to use this, you would have to add these terms. But this is generally how these equations look like. And then we have in this equation, so if we derive now the equation for the mean, then we have two terms which are unclosed. One is this gradient transport term, and we said yesterday we typically use a gradient transport assumption for this, and we'll see later on that this is not always a good idea. But let's say we do this now, and then the second one here is the chemical source term. And that's the one we have not really talked about. So here we just want to see what the error would be if we don't worry about modeling. So how does this look like? We said for a one-step global chemistry, the source term kind of looks like Y fuel K, let's say, not K, let's say B, pre-exponential factor times YF times YO times, let's say this is, let's say times a coefficient. I don't care about this. So here really these should be concentrations, and here we have now, or maybe let's just write it. Density squared divided by WF and WO, and then we have maybe exponential of minus E divided by RT. So if we want the average of this, then that would be the average of this entire thing, okay? So this would be average of this entire thing. And then we would have to, like we did before, introduce here the Reynolds decomposition, which would give us something like y mean plus y prime, y mean plus y prime. Here we have t plus t prime, and so on. And you see, you get an awful lot of correlations. So let's say we want to neglect all these correlations and just evaluate this with a mean. I could say, so maybe a model. So I could say my model says I want this to be YF, and then YO, and then rho mean squared divided by WF WO exponential of minus E divided by RT mean. So this means I don't close anything, I just evaluate the source term with the mean quantities for which I have equations, okay? So I could do that, and then here we want to see what's the error we would make. So this is the assumption I just made. The mean source term is the same as the source term evaluated with the mean quantities. Okay, that would be one way to do it. So you see here, this is what I just wrote down actually, where this here is so we assume maybe this is a lean mixture. Lean mixture means the fuel mass fraction is small and the oxidizer is large, so the oxidizer doesn't matter. Then it's really a first order reaction. And then Y fuel expressed by a coupling function is TB minus T. Okay, that's just using a coupling function. And all the coefficients are in this B here. So you see the correlation now here of these temperatures. We can insert this. And if we do that, then we see is difficult because this is not just a nonlinear term. The argument here also is nonlinear. And so just to see what the error is, we can do a Taylor expansion here of this minus E divided by RT term. Then we get minus E divided by RT mean plus, and then or minus E by RT squared times TB minus T, and that should be T prime here. So that's an approximation for this. If I plug this back in here, I get two terms. One actually evaluated at the mean, and this one here would be the fluctuation. And then here also I have in the pre-exponential factor, I have a fluctuation. And then I can write this then as the source term evaluated with a mean times a correction factor that depends on the fluctuation. And if I set the fluctuation to 0, then if there are no fluctuations, maybe in a laminar flow, then here evaluating with the mean is correct, and otherwise it's not correct. And then you see that here, for example, if the temperature gets close to the adiabatic flame temperature, then, so this is what we have actually in the reaction zone, then this term here becomes very large, and this one here goes to 0, okay? And then secondly, we see here that this term E divided by RT is roughly of the order of 10 typically. And then T prime divided by T, maybe that's 10% to 30%. If we plug this in here, then this here alone gives us a factor of roughly 10. Okay, so this means if I approximate for typical flame the source term just by the mean and neglect the fluctuations, I'm off by an order of magnitude, factor of 10. So that is very large. So that's not appropriate. Okay, that's all this tries to say. Here's another example. This is the equation for the mass fractions. Okay, and again here we have the scalar flux term here, and then here we have the chemical source term. And for the scalar flux, maybe we use this, but we don't even need to. What I want to do here is I want to write this equation for isotropic turbulence. Isotropic turbulence, we said the velocities have to be 0, the mean velocities are 0, so this thing goes away. And we said also gradients are 0 here, and so if gradients of mean quantities are 0, then also this is 0. And what remains is just this term and that term, okay? And so all this says is here dy dt is equal to the mean source term. And now we want to evaluate this from DNS. So this is a direct numerical simulation. It is a very simple one. We did this many, many years ago. And so here we start out. You see here, and maybe in the center, here's oxidizer, and here is fuel. And then in between, you have stoichiometric mixture. So the lines you see here, there's a green line or something. That is the line of stoichiometric mixture, and the color is the temperature. Okay? So you see, while this proceeds, the temperature here, sometimes you get local extinction, like here. And But most of the times, the temperature is high, around stoichiometric, and then while mixing here in this box proceeds, more and more fuel and oxygen are consumed or converted to products, and the average temperature in the entire box goes up. So this is the average temperature in the entire box as a function of time, and the symbols here are from the DNS, okay? And then if we solve this equation here, just using the source term, evaluated with the mean quantities, then this is what we get, okay? So it's not just a little bit off, it's totally wrong, okay? The temperature never goes up, or it goes up just very, very slightly, okay? And then if we use a simple flamelet model, then this is the symbols here. The solid line is from DNS, the dashed line is from the simple flamelet model. And you see that's actually is not perfect, but it's not so bad, actually. So closure using just mean values does not work. Okay, so we need to worry about how to close the chemical source term. And here, as I said, I want to show you just a few examples for how that can be done. This here is from the Fluent code. Maybe it's not the latest version. This might be here. This is Fluent version 12. And this is a window here that you get for species model. And then you can say a species transport. And then here the material. And then you can choose a turbulence chemistry interaction model. And we have here 4 different models which you could choose. They're different complexity. And you see, I call this here model 2, 3, and 4, and 5. And there's one more that I'll show you here in the following, because it's kind of the basis for all of this. So one of the first models here was modeled by Spaulding. It's called the Eddy breakup model. The idea of the model is that, so this is for premixed flames. He was interested in engines, premixed spark ignition engines. And so he came up with a model that's really based on the idea that the chemistry or the proceeds by mixing. So that mixing is the controlling step, and then the chemistry is just whatever mixing dictates. So we assume very fast chemistry after infinitely fast chemistry after the fuel air mixture is preheated, and then the combustion process proceeds by the breakup of these eddies, which is then really the mixing process, and so this is called here the EBU model. The chemical source term is then modeled like this. We say really the chemical source term is controlled by mixing, is by preheating the cold fuel air mixture. And so it proceeds with a turbulent time scale. What is a turbulent time scale? Epsilon over k is a turbulent time scale. Okay? So basically you could just say leave it at epsilon over k, but then there would be a little problem. Here's the problem. If I look at turbulent flame, then maybe I have turbulence everywhere, but if I'm far ahead of the flame, then maybe the process variable or temperature is just, or product mass fraction. If I'm way ahead of the flame, then the product mass fraction is just 0. And if, then I have a turbulent flame, and I'm behind the turbulent flame, then the product mass fraction somewhere way behind the flame, it's equal to 1. Okay? And then in between, you have somehow a turbulent flame. But fluctuations at some point go away. At some point they start, at some point they go away. And obviously, in this region, there's no chemistry. And in this region, also there's no chemistry. Okay? So the idea here is to then take that turbulent time scale, epsilon over k, and just weight it with the fluctuation of the product mass fraction. which means then in this case, this quantity here, y prime, this is the fluctuation, that is 0 in the burned, it's 0 in the unburned, it's only non-zero in the flame. So ahead of the flame, you have turbulence, maybe mixing the product a little bit in the unburned, and that will then make the fluctuation non-zero. This is when chemistry starts. It will proceed here with this mixing time scale, and at some point, everything is converted. The fluctuations again go to 0. These fluctuations go to 0, and then the source term gets 0 again. Okay? So that's how this model works. And so it has some interesting features that, that are not so wrong. But some of the issues are that, that it really doesn't depend on chemistry. If it doesn't depend on fuel, if I use a different fuel, I get exactly the same thing. If I have EGR, for example, the model doesn't know this, okay? It doesn't know that chemistry becomes slower when you have EGR, exhaust gas recirculation, or if I have lean or rich conditions, also the model doesn't know this. It just says the chemistry is always fast no matter what. So, so that model has its shortcomings in that way, but also in addition to this, it cannot be used for diesel engines, where I have very rich mixtures which we know are not reactive, or very lean mixtures which are not reactive. So the model has then been taken here by Magnussen, and so they developed what's called the Magnussen model, or the Eddy-Dissipation Model. And now you see already it's very, very hard to keep track of these names because they're all the same, for me at least, but they all mean something else. Okay, here. Eddy breakup model, Eddy dissipation model. So, and there will be a similar name later on also. So the Eddy dissipation model makes same assumptions. The chemistry is very fast, and the chemistry comes from mixing. And so again, we just use the chemical source term, should be proportional again to a mixing timescale, or inverse of a mixing timescale, which again is epsilon over k. But then this switching on and off of the reactions is done here with these, let's say, 3 terms. So these here are the reactants, fuel and oxidizer, and then P here is the product. And so here we just evaluate these 3 terms, the product, the oxygen mass fraction, fuel mass fraction, and the product mass fraction, and then we take the minimum of these 3 to provide a weighting here for this time scale. And what does this mean? That means if I'm in the lean part of a flame, there is no oxygen, there is no fuel anymore, okay? So I shouldn't have any reactions. Let me just draw it. So if I look at, let's say the Burke-Schumann solution, or something close to the Burke-Schumann solution, then this would be the product mass fraction. And chemistry essentially happens here in the thin region. So this is where the reaction zone. And this is here, I have no fuel. Sorry, here I have no oxidizer, and here I have no fuel. Okay? So, so then with this expression, in this region, the oxidizer is 0, which means this here, I evaluate for the oxygen, would be the smallest of the 3 contributions. So the chemical source term would be 0 in that region. And then on this side here, there's no fuel, and then this evaluated for the fuel is 0. So again, this is 0. And if things don't burn at all, everything's cold, then a diffusion flame doesn't burn. And it doesn't burn here in this case then, it has no product, and then it would also be 0, okay? But if it is burning and we are close to the reaction zone, then you might have a little fuel and a little oxygen, and you have a lot of product, let's say, a little fuel and a little oxygen, then this is non-zero, and you can evaluate the source term, okay? So that's kind of the idea, that you need to burn you need to have fuel, oxygen, and it needs to be hot. That's basically what this says. And if that's the case, then reactions proceed here with a turbulent timescale. So, well, this just discusses this here again. This discusses exactly what I just said. But at the end of the day, you get a model that is applicable for diffusion flames. So again, it's controlled. The chemistry is controlled by mixing. It assumes very fast chemistry, infinitely fast chemistry, maybe, and it can be used for. It was really developed here for non-premixed combustion. It can also extinguish, for example, or do only partial conversion if the time scale is too short and the chemistry doesn't happen. So once the product mass fraction is 0, then things don't happen anymore. And then, well, it's simple. But the issue is it does not cannot be applied or does not predict anything that is not in equilibrium. So, for example, NOx formation and things like that. And also, it doesn't, so fuel consumption here is overestimated, and the temperatures are not predicted well. Why is that? Because in reality, you have the fuel and you first form CO and hydrogen, and then the hydrogen and CO are converted to products. And here everything just goes from reactant to products. So these are two classical models. Here's another model which was called here number 3 is called Finite-Rate-Chemistry model. And there are some other fancy names for this, but basically what Finite-Rate-Chemistry model means is what I called no closure in the beginning. Okay, this is exactly evaluating the chemical source terms just with the mean quantities, which works well if for very, very small Damköhler number, but it doesn't work for a normal flame or combustion case. Okay, so you see here, this just evaluates everything just with the mean quantities. So here again, this is appropriate if the chemistry is very, very slow, and mixing is very, very fast compared to the chemistry, but otherwise it would not work. But that's a method that's still often used, because you don't need to decide on premixed or non-premixed, but at the end of the day, I showed you in the beginning, it cannot give you any reasonable results for a normal flame.
Can we just introduce mixing using partially stirred reactor model?
Pardon?
Can we just introduce the mixing into the reactor using a partially stirred reactor model?
So the question is, can we introduce mixing with a partially stirred reactor model? So that is something like this next this next thing. That's a no, maybe not this, but I'll come to this. I mean, there are ways that try to overcome the issue that this has basically no turbulent closure by using these partially stirred reactor models. And the issue is that I don't fully understand these. I'll show you one of these models, but I don't understand. To me, this sometimes seem very empirical. They're not general. They wouldn't work for any situation. So they have to be modified for every situation you're considering. But again, maybe I just don't understand it right. But I'll come to this is the next thing I'll talk about. Okay, so then there are combinations of these here. Eddy Dissipation Model combined with the finite rate chemistry, and here the idea is to not really blend. This here, by the way, I understand, because this says I have one asymptotic limit, which is finite-rate chemistry. And I have an, which is, I don't need closure. It's very slow chemistry. Sorry, very slow chemistry. And I have the other asymptotic limit, is very, very fast chemistry. And I have a model that's formulated for both these assumptions, one for each of these assumptions. And now I just try to blend these together. That's something I understand. I mean, I can really understand. So here, the idea is I have one reaction rate for assuming infinitely fast chemistry. I have one reaction rate assuming very, very slow chemistry. And then I just say, I always pick the smallest one of the two, because that must be the rate controlling process. And that's just what it is. So the disadvantage here is it doesn't really explicitly model the turbulence chemistry interaction, but in some way it considers both of these limits, both of the asymptotic limits. So, and most of the time probably the truth is somewhere in between, which means maybe this is good for the asymptotic limits, but if the truth is in between, maybe then it's also not exactly right. So this here is, I think this is a model like you described it, with a partially steered reactor. Was this called? So now we had the Eddy Dissipation Model, Eddy Breakup Model, and now this is called Eddy Dissipation-Concept. So the idea here is that you define a length scale here over which these reactions should happen. So this star here stands for the fine scale. And so this is a length, and it's defined somehow like this. You see it's a small scale because the viscosity appears here in this thing. There's a coefficient which is given here. This is what fluent uses. And then if I take this cube, that gives me a volume. So that's the volume over which the reactions happen. And then here I define a time scale also for this. And you see I use same quantities to define the time scale. So also this is a small scale time scale. This here is actually the Kolmogorov time scale. So then what I do is I solve just a homogeneous reactor. Let's say in each cell, I assume the cell is a homogeneous reactor. And I want to do a simulation for a certain time step. So I just do a numerical integration of that time step as a homogeneous reactor. And I get a new set of mass fractions here at the end of the time step. But I don't use this because I guess the assumption is they say maybe not everything was mixed during that time in that cell. And so I use this new value just to do a relaxation. So I have the chemical source term says is y star minus my present value divided by a time scale. And if this time scale here is very, very short, meaning I have fast mixing, then it means everything mixes within this time step, and I will reach the y star. But if mixing in the cell here is very, very slow, then the source term will be small, and I will advance my mass fraction towards this y star, but I will not reach it. I will just go towards this, but I will not reach it. And the next time step, again, I do the same thing, okay? So that also, this model also, it kind of does a chemistry step, a finite rate chemistry step, and it also tries to do, consider the small scale mixing time scale. And so I haven't looked in very much detail at this, but for this model here, at least, it's very easy to understand that you satisfy some asymptotic limits. So that's a nice feature of this. Whereas here, I don't necessarily see this, but I'm not saying it's not there. So here I just wanted to show you these are the options you have in a commercial code like Fluent, and you don't need to do anything. You just need to click on the button, but still you need to be able to choose. I mean, you need to have some knowledge to know which model to choose at this point. So the different issues. So one of the issues here is that because you need to solve these the finite rate chemistry at each time step in each cell, it means if you have a normal chemical mechanism or reduced chemical mechanism with more than a few species, that is also very very expensive. It also turns out the equations are stiff. Maybe here because this approach is zero or so, but it can become stiff. So anyways, these are the options you have here. Just Arrhenius equations with a mean, but that means the turbulence is not considered at all. And then you have here these choices of this combination, which is basically a local choice, infinitely fast or infinitely slow chemistry. And then this here is just mixing rate controlled. These models are actually still used a lot in engine simulations, even though they're known to not really produce very good results. And then there is this Eddy Dissipation-Concept here. One of the things that's interesting also here with this, I didn't say this, I forgot to say this, with this Eddy Dissipation Model here, which originally was formulated for diffusion flames, one of the issues is that you have this B here is just a coefficient, is a model coefficient. How strongly should I weigh the product mass fraction compared with the oxygen and fuel mass fraction? That's B, and A is just a coefficient in front of the whole thing, okay? Both of these coefficients are not universal. They have to be tuned every single time you do a simulation. So the typical way here would be you want to do a simulation for an engine. This is where this model is often used. You have some data for the pressure, and then you do a simulation, and then you tune these two parameters. It's always hard to tune two parameters at the same time. If you have a lot of experience, maybe it's easy, but if you just have to tune one parameter, it's relatively simple, but tuning two is difficult, but that has to be done. So once you tune these, then you say, okay, for this engine, for this operating point, this is not bad, and now I can do parameter variations. Now maybe you inject a little earlier, a little later, or a little more EGR, a little less EGR, then you do a parameter variation just around this point. So that's the tuning. Some of these models have tuning parameters, others don't really have tuning parameters. And tuning parameters have the advantage that you can, I mean, combustion model, there's no perfect combustion model, and tuning parameter has the advantage that if you have data and you want to just look at the parameter variations, you can actually make the model work and then do parameter variations based on that. But then sometimes the model parameters, they have to be tuned also. I mean, without this tuning, the model is really bad. Okay, so these are some of the models. So before I'll talk about the more complex models, I want to say a few words here about statistical methods. So this follows here very much here the Turbulent Flows book by Professor Pope. And it's just an introduction to statistical methods here that introduce different concepts that we use in modeling. So for example, we want to talk about PDFs, probability density function, and in order to define these, we need to introduce this cumulative distribution function, and for this we need to introduce these terms. So we just go step by step to introduce these different terms. Okay, so the first here is the concept of the probability. And in order to define a probability, I need to define an event for which I want to measure a probability. So for example, if I look at a velocity, so I measure locally velocity, how do I define a probability? Can I say, can I talk about the probability of the velocity being 1 meter per second? So if I measure the velocity, I mean I have a turbulent flow, and I measure the velocity at one point many times, 100 million times, and then I can evaluate what is the probability that the velocity is 1 meter per second. Is zero, okay? Because it is never going to be exactly 1 meter per second. Maybe it will be 1.000001, or it will be 0.9999999, keep going. But the probability that you hit exactly one it's impossible. Okay, so you need to define events for which you can say true and false. Okay, so is the velocity larger than 5? Each single experiment I can say yes or no. Okay, is it smaller than 10? Each single experiment I can say yes or no. So that's how we want to define an event. Here we want to define what's called a sample space. And then I compare a measurement with the sample space. So, for example, I want to find the probability of the velocity less than 5 meters per second. I do many experiments, and 40% of the time it's smaller, 60% of the time it's larger. Then I define an event. When is my event is the velocity less than 5 meters per second? And the answer is for 40% it's yes. So the probability of finding this being less than 5 meters per second is 40%. Okay, or the probability that my event is true is 40%. So that's shown here, and then I can say I have an event A here is u. The velocity is smaller than VA. VA is also a velocity, but that's my sample space velocity, the one against which I compare. We typically give that a different symbol. This is the random variable that I measure, and I can also look at an event is the velocity in between these two values, larger than VA, smaller than VB. And so that's the event, and then the probability here is just defined as the event being true or false. And so the probability is always between 0 and 1. Either I have no event which is true, or all events are being true, and so it's never negative or larger than 1. Okay. And 0 means it's impossible, and 1 means it's certain. So that's the probability. So we define an event which is true or false, and then we define the probability of this event, and then from this we define the cumulative distribution function. So if for the probability I've defined one event, so the velocity is less than 5 meters per second. But I could also evaluate, from my data set, I could also evaluate probability if the velocity is smaller than 6 meters per second or 7 meters per second, or any given value of v, okay? And so the probability can be expressed as a function of the sample space variable. And if we do that, then we just call it the cumulative distribution function. So the cumulative distribution function is just the probability of all possible values of the sample space variable. So let's say 5 meters per second, 6 meters per second, 7 meters per second, and this is the probability. And then so if I measure the velocity, maybe the velocity is always between 3 and 7, then the probability of this less than 5 is maybe 20%, less than 6 is 40%, less than 7 is 90%, and less than 25 meter per second is 100%. Everything is less than 100%. So then if I just do this for every single value, then I get something like this. Okay, so that's the cumulative distribution function. And the cumulative distribution function evaluated for a certain v just gives you the probability that the velocity is less than that value of v. So so that means that so the cumulative distribution function shown here, it has a few properties. First of all, the u less than minus infinity is impossible. Okay, so f of minus infinity is 0, so it always starts at 0. The probability that the velocity is less than infinity is 1. Okay, so it always goes to 1. And then in between it goes from 0 to 1. And because the probability that the velocity is less than 5 is always smaller or equal than the velocity being less or equal a larger value of the probability variable, it's a monotonically increasing function, so this cannot go down. Okay, so it's monotonically increasing. It can be flat, but it can never go down. Okay, so that's basically then is the probability, or we call this the cumulative distribution function. And one of the things that is that's interesting here is, so if you now think you have done thousands of different measurements, and then where would you find these measurements here in this plot? Where would you find most of the data points in this figure? The steepest slope, right? Because that would the more data points the more data points. So let's say all the data points would be at v equal to 0. Okay, all the velocities would be 0. Then this thing would look like this. It would go flat at 0, 0, 0, and then it would go to 1, and then it would stay at 1. So the steepest slopes always gives you the highest number of samples. So it would be interesting to have a function that has the maximum value where you get most of the samples, and that means steepest slope means we just take the derivative of this function, and that has that property. So if we take this, the CDF, if we take the derivative of this function, then it looks like this. And now here where this function is the maximum, that is where you get most, you had most of the samples. And so this is just the derivative with respect to the sample space variable. And so this is what we call the probability density function. Okay? So the probability density function then, it has also a few properties which come from just the properties of the CDF. First of all, it's because the CDF is monotonically increasing, the slope of this is always larger or equal to 0. So the PDF is always larger or equal to 0. It cannot be negative. Okay? And then also, you can show this easily from this here. It satisfies the normalization condition, or let's say it has to satisfy a normalization condition, which is that the area under this curve is equal to 1. Okay, so this can be easily shown here from the definition. So is f, if f is equal to the f dv, then the integral of f dv is equal to the integral from 0 to minus infinity to infinity. Then this is equal to the integral of df dv dv, and that's equal to f between minus infinity and infinity, and that's equal to 1 minus 0, so that's equal to 1. So the PDF, that's very, very important. The PDF always has to have area of 1. And we were just talking yesterday with someone The PDF sometimes is evaluated by binning, by just counting how many times you measure something in a certain range here of the sample space variable, and that gives you an approximation then from the data for the PDF. But it only gives you that if you normalize it. And I remember I had a student who was working for a long time on a model and couldn't figure it out. It never worked until we realized that the student had forgotten to normalize the PDF so that it has that the area is equal to 1. So always remember this. It might save you some time. Right. So that's very important. And then also for minus infinity and plus infinity, the function has to go to 0. Okay, so that's the PDF, and then the question. I mean, we discussed the question: how can one evaluate this? And really, if one doesn't want to do binning, one way to evaluate it is really to determine the CDF first, and then take the derivative here of the CDF. That's one way to do it. So let's see. So we're talking about we're talking about the probability density function, and we're also interested in probabilities. And what we said earlier was that that the probability, for example, of finding a value between less than a point, that is just the value of the CDF. That's the probability of finding U smaller than VB, and this here is the probability of finding U smaller than VA. So this means if I want the probability of U being in this interval here, that is just f of VB minus f of VA, okay? And you see that this is nothing else here than the integral of the PDF between these limits, okay? So the integral of the entire from minus infinity to infinity of the PDF is always equal to 1. But if I integrate the PDF between two values of the sample space, so the area between these two values, that's the probability of finding the value in this interval. Okay, so that's a very nice property of the PDF. You see immediately where the probability is, what probability is high and what probability is low, and so on. Okay, so then that's CDF and PDF, and I want to give you a few examples here for functions that are often used. So the uniform distribution here means between A and B, I have equal probability for any value, and then the PDF looks like this. This is the functional form, okay? So that's one. Then exponential distribution is another one that sometimes occurs, not here now in our course, but you can always plot here somehow the PDF and also the CDF. And then this is the one that's most common here is the Gauss distribution, the normal distribution, or the Gauss distribution. And the Gauss distribution, it's I think we have the formula on the next page, but it has two parameters, a mean and a variance. This is the so-called standardized, which is normalized such that the mean is at 0 and that the standard deviation is equal to 1. And then this is how this function looks like, and this is the CDF. Now, you see this here, this is the so in Germany, we use the euro as a currency, but a few years back, we used the German mark, here, Deutsche Mark. This is the 10-mark bill, and you see this is Gauss, and you see here this is the Gauss function, and here it even has the formula. So as a German student, this is the one thing you never had to memorize, because if you're in an exam, and you just have some money. If you had no money, it's a problem also, but if you had some money, then you could also look this up. Okay, so they replaced this, and the euro is more boring. It doesn't have mathematical functions. Doesn't have mathematical functions on it. But the Gauss distribution is that's a distribution that happens very often. There is something called the central limit theorem, which pretty much says that if you have a random process, and that random process has a certain distribution, doesn't matter, some distribution, could be any one I just showed you. And the central limit theorem says that if you have many processes interacting, then it doesn't matter what distribution they have. But if you have many interacting, then the result will always be a Gauss distribution. Okay? So an example is this. Now I forgot the name of this thing, but you know this board. You have a slanted board, and then you have nails in many nails in the board, and then you put a little ball top, and then it bounces off the nails, and it just keeps going down, and then it ends up somewhere in the bottom. You know these? Yeah. So that, if you do this often enough, you always drop in the ball in the center, and it will always end up somewhere else. At the end, you will have a beautiful Gauss distribution. There is one of these in the Exploratorium in San Francisco. So it just drops, a lot of balls, and it has on the board, if I remember right, it has a perfect Gaussian drawn, and you just drop the balls, and then you get a perfect Gauss distribution. So that's basically the result of the central limit theorem. That's why in processes in nature we find the Gauss distribution very, very often. I mean, it's very typical. Also for turbulence, very typical. Although in turbulence, the very large departures from the mean, very small or very large, they sometimes behave a little differently. But overall, Gauss function is normal distribution is found a lot. Here's another one, the delta function. That's something we'll use later on. The delta function just means basically the delta function is nothing else than an infinitely large value at a certain position, and it is defined to have if I integrate it, to have an area of 1. Or if I have a double delta function, so I have two delta functions here, the sum of the two curves here, or the areas under these curves is 1. So you can think of this as an area that is very, very, very narrow, but very, very, very high. Okay, so or say you have a Gauss distribution where you make the standard deviation smaller, 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 and let the standard deviation go to 0. That gives you then a delta function. Actually, mathematically also is much, much easier to deal with a Gauss function than delta function. You can mathematically deal with, you can take derivatives of delta function, but you have to be very careful. So we have published papers somewhere where we use the delta function, and so the integral of this is then the Heaviside function, which has these steps here, and we have published papers where we just say, okay, these are all Gauss functions with 0, or with standard deviation goes to 0. And then the integral of the Gauss function here is the error function. Okay, so here, this is how it's defined. So here is the value goes to infinity for this value, and it goes to infinity for this value. This is what this arrow here denotes. But the width of this is just such that you get the integral gives you the strength, and the strength or the probability of finding this value, and the probability is then here this p. So p is probability of finding this, 1 minus p is the probability of finding that. And so this here is, for example, if you have only 2 possible values at all, then this is what you have. So for example, we'll see later on, we'll have a scenario where the only two possible values we want to allow are 0 and 1. Okay, so then you would have one of these at 0 and one of these at 1, and then the strength of both of these then shifts depending on what you do. Okay, so let's say we know the PDF. That is very nice because from the PDF you can compute or determine all the moments of a function. You can determine the mean, the variance, and the third moment. For the standardized functions, then that would be the skewness, for example, or the kurtosis. So you can determine all these moments, and so this is how you do it. So the PDF times, so if I want to get u to the nth power and the mean of that would be the nth moment of this of the velocity. Then I just evaluate it by v to the nth power times f of v dv. Okay, so this integral here always gives me the average of this function. So this is true also for any function of v. So if I have a function of v and I want to evaluate the mean of that, so this could be the chemical source term as function of temperature. So if I know the PDF of the temperature and I know the functional form, like here, the exponential function, for example, if I want to get the mean of this, then I can also evaluate this like this. Okay, so once you have the PDF, then you can, any statistics you can determine from this. So this here is something we often use, v times f of v dv, that just gives you the mean. And then u minus u mean, that would be u prime, that's the fluctuation. And that also, we can get the mean of this. So here, for example, u prime square mean, the variance, that would be just u minus u bar, that is u prime, squared, and then mean. And then I can just evaluate it like this. Okay, so this for any function, this works. Okay, so these are the PDFs. And then in combustion, very often, we are worried about what's called joint PDFs. So very often we have a function not only of one variable, but of many variables in combustion. For example, a chemical source term, you see here, that is a function already of 3 different variables, fuel mass fraction, oxygen mass fraction, and temperature. So the joint PDF does nothing else, or here's the joint CDF. It just looks at 2 events at the same time, okay? So earlier we said this one event is true or false, and here we just say, we look at both events. If both events are true, then it's true, and if one of them is not true, then it's false. Okay, so it's very simple. It's just the same thing, really. So the CDF now, here's a function of 2 variables, and it just tests, it gives you the probability that both of these conditions are true at the same time. Okay, so that's very useful. So let's see if so this here then says that so I have this function, the CDF, as function of 2 variables, and I can evaluate this here, for example, at v1 equal to minus infinity, but because that is not possible, v1 u smaller than minus infinity, that's always 0. Okay, so if one of these is chosen to be minus infinity, it's always 0. But what's more interesting, if I choose v1 to be infinity, then the first condition is always true, and that then just gives me the CDF of the second variable. Okay, we call that then the marginal CDF. So f12 of infinity and v2 is equal to just f1 of v1. Oh no, f2 of v2. Same thing, of course, for the other one. But that's the marginal. So we can always, that's interesting or important, if I have a joint CDF, if I have that, I can also get I can always get the marginal of each individual variable. And then if I take the derivative in both directions, that's the joint PDF then. And the joint PDF has the same properties as the PDF. I can integrate that between two values in each direction, and that gives me the probability of finding something within this square here. Okay. Again, the joint PDF, just like the marginal PDF, is always larger than 1. It always has to have satisfied the normalization condition. This time now in all directions. So it's a multidimensional function, and if I integrate this over all the space, then the integral has to be 1. And again, if I integrate this over one direction, so if I integrate this over V1, I get the marginal PDF for V2. Okay, so maybe I think it's time for a break. Maybe we'll stop here, and then we'll continue at 10.